Welcome back to the open session of the PAC. We start with the first of three presentations. This will be given by Eric Boutier on a proposal to measure the beam charge asymmetry for DVCS at class 12. Please, Eric.
Thank you. So good morning and good afternoon, everybody. I am presenting this proposal on behalf of the class collaboration and my co-spokesperson. The experiment is sketched in these three pictures. We want to learn about the internal structure of the proton. For this purpose, we would be using polarized electrons and positron beam to scatter of the proton, and the reaction product will be measured in the class 12 detector. More specifically, we want to measure the beam charge asymmetries for the production of photons on unpolarized hydrogen using the class 12 detector and a beam energy of 10.6 GeV over a data taking period of 100 days. We would measure the azimuthal and T dependencies of BCAs over a large space in X Bjorken and Q square. This proposal follows a letter of intent that was proposed to PAC 46 and which was discussing the perspective of an experimental program with positron beam at Jefferson Lab. It was discussed in terms of 7 mini-letters of intent. Following the encouragements of the PAC 46, we are coming back today with two different proposals about DVCS on the proton. So the outline of our presentation is the following. I would like first to remind about the importance of generalized parton distribution, then to discuss a little bit more the case of beam charge asymmetries before going into the experimental details, and finally going to my summary. Generalized parton distribution offer an unprecedented way to access the spatial distribution.
It's only me that I don't see your slides moving forward at all. The first slide.
It's moving for me.
And Marcus, is it moving?
It is moving.
Yeah, okay.
It is moving, yes, Patrice.
Yeah, okay. So, yes. So we have a very unprecedented access to the spatial distribution of partons. GPDs can be seen as a generalized form factor representing the distribution in the transverse plane of partons carrying a given longitudinal momentum fraction of the nucleon. But not only, they also encode the correlation between the partons, and they can give us you can gain information about the dynamics of the system, which is, for instance, the angular momentum of the quarks or the distribution of the force inside the proton. So the golden channel to measure these PDs is to do electroproduction of photons, which gets a contribution from the DVCS, the process we want to know, and the Bethe-Heitler process, where the photons is emitted by the incoming or outgoing electrons instead of the proton. This process is interference give rise to 5 different contributions that you can distinguish. That distinguish themselves also by the sensitivity to the polarization of the beam or the charge of the beam. The Bethe-Heitler is known, and if you have only polarized electron beam, you would measure from the unpolarized cross-section or the difference of polarized cross-section, you would measure a combination of DVCS and interference contribution. If instead you have also positron beam, you can do comparison, and then you can isolate the interference contribution, which means that with combining polarized electrons and positrons, you can separate the phonon contribution to the cross-section, which is the best that you can do experimentally. GPDs enter the cross-section in terms of Compton form factors, and those Compton form factors have a real part which goes into the polarization independent part of the cross-section, and an imaginary part which goes into the polarization sensitive part of the cross-section. At leading twist, DVCS access a combination of those Compton form factors, and you have here a bilinear combination for the DVCS amplitude and a linear combination for the interference amplitude. You can see just by comparing these two expressions why it is already important to separate the interference from the DVCS contribution, where you have here in this interference contribution a much a less convoluted information about the Compton form factors. Experimentally, we obtain information about the Compton form factors from the azimuthal distribution of the cross-section. The DVCS cross amplitude is related to the real part of one Compton form factor, and at twist 2, the polarization sensitive part of the DVCS is 0. It only appears at the twist 3 level. And you can see here from the dependencies in the out-of-plane angle, once again, it is important to separate the interference and the DVCS contribution, having a very clear signal connected to the interference contribution. One example of the interest of the physics can be seen here in the second momentum, in the second Mellin moment sum rule, especially more specifically in the skewness dependency of this momentum sum rule, where coefficient D1 appears, which this coefficient that can be connected to some distribution of forces inside the nucleon. Unfortunately, the actual knowledge of the GPDs, experimental knowledge, is far to allow a complete experimental determination of this sum rule, but we have other ways to access to that, and we can take advantage of the dispersion relationship between the imaginary part and the real part of the Compton form factors, and extract from the D term which is represented here, extract the same coefficients. Obviously, to get that, you need to have a very good measurement of the real part of the Compton form factor, which once again you can obtain nicely with the interference contribution. So what we would like to measure, we measure to propose the unpolarized charge asymmetries, which will be sensitive to the real part of the Compton form factor. We want to measure also the polarized beam charge asymmetries, which provide you another access to the imaginary part of the Compton form factor, an access which is different from the one that you can obtain with the beam spin asymmetry. And we could also investigate the neutral beam spin asymmetry, which is directly connected to higher twist effect. You have here on this plot prediction, model calculations of the unpolarized and polarized beam charge asymmetries. The same different color for different T and different lines for different Q square. You can see that we have a variety of amplitude and magnitude for these observables, and that we can measure in one shot with a class 12 detector, thanks to his very large kinematics coverage. And you have here the sensitivity to, of course, these predictions are sensitive to the model of GPDs that you are using. And you can see here by comparing projected data with respect to the model predictions that we have some discrimination sensitivity, and which that the power is diminishing as far as soon as you go to IQ square, IX Birken, and IT. There exists today at Jefferson Lab a very large program of an approved experimental program of DVCS measurements. And one can ask in this context, what would be the benefit of having positron beam in addition to these data? And this is what we have been trying to, the question we have been trying to answer here by extracting the real part of the Compton form factor H from a set of observables with or without the positron beam. And the net effect is that you have an improvement of the statistical and the systematical error on real of H. Systematical is, you can see that by comparing the position of the blue point with respect to the line, which is the model. And so this systematical, this reduction of the systematical effect is really due to the fact that you access an observable which is directly proportional to the real part. Statistical effect is a direct, is also connected to that, but it's is also it's much more a reduction of the correlation of the between the Compton form factors in the extraction process. The implementation of positron beam at Jefferson Lab is sketched here. You would take the electron beam at 123 MeV and transport it in a different area where you can produce the positrons, collect them, manipulate manipulate the emittance and re-inject them into the in the injector to be accelerated in the main complex. This scheme allows us to different operational mode, going from low intensity but high polarization up to high intensity but no polarization. Simulation of the propagation of the beam inside the machine are suggesting that the positron beam at target would have the same momentum dispersion of the electron beam, but would have a larger beam emittance, which would be resulting in a 2 to 3 times larger beam spot. And for this, we anticipate to avoid any interaction of the beam tails with the structure frames, we anticipate an increase of the transverse side of the target. The experiment would be done with a class 12 detector, with a regular detector arrangement, operating in outbanding mode, and with a luminosity of 0.6 10 to the 35, which has been demonstrated. There is no difference between electrons and positrons in the transport of the beam in the beam line, nor in the related detector, related background in the detector. And the beam diagnostic are expected to operate similarly for electrons and positrons. You have here an example of the kinematic coverage that could be achieved, and this I should insist, these are real data coming out from the subset of run group A data in the same operating mode that we are suggesting to use. You can notice the coverage in X-Birken and Q-square, and you can see the shadowing effect here and here about from the coils and the angular coverage of the forward tagger. We should be careful that we could have false asymmetries, and those false asymmetries would be generated by the effect of the magnetic field on the trajectory of charged particles. In order to study that and to later correct that, we are suggesting to take data with by alternating the polarity of the solenoid field. And in addition to that, we would also measure simultaneously to DVCS elastic scattering at low Q square, that is in range, which would help us to control those effects and also provide a link between electrons and positrons. We have also we always measure, we have been measuring for a long time beam spin asymmetries, where many effects are cancelling out. Beam charge asymmetries are different from beam spin asymmetries, and they are much more comparable to a relative cross-section measurements, where some systematical effects cancel out, but others are still there, and you have to control and monitor them. So if you would like to, if you want to minimize the systematic effects, so in order to do that, you would expect to have the same beam quality, the same detector, and also the same statistics for the dataset in electrons and positrons. We already see that for the detector, it's not quite true, so we will have to implement corrections to the raw asymmetries that we are going to measure, and correction which are connected to the differences in electrons and positrons, in efficiency and solid angle. And the accuracy of the knowledge on these coefficients will directly enter into the systematic uncertainty. In order to minimize the effect other effects which are essentially connected to the global beam property, we are suggesting to take DVCS theta with the secondary electron beam, which is also simultaneously produced at the positron production target. The target when you put the primary CFFS beam onto a target, you would produce electrons and positrons at the same time, but the system will select one or the other polarity to transport.
You have 5 minutes left.
Thank you. Perfect. So you have here the beam time request, which is detailed here in this table. So we are asking for a total number of 100 days of beam time operating class 12 with 55 nanoamp for electrons and positrons. And the distribution of this beam time is 80 days for physics and 20 days for commissioning and calibration. And we would be using 2 beam energies, 9 days at 2.2 and most of the year remaining, all the remaining time at 10.6 GeV. The experiment, the data that we would obtain, you have here just a sample of the expected experimental data. We would have 15 beams in X-Bird Cannon Q² and 6 beams in T, which is 80 azimuthal dependency like that per observables. And of course, depending on the Q², the statistical error bar will change. So to summarize, we propose to measure beam charge asymmetry for the DVCS reaction of protons at 8.6 GeV with class 12 and using the secondary polarized electron and positron beams produced at a paper-like positron source, and this for 100-day data taking period. The separation of the DVCS and interference amplitude, reaction amplitude really provide an ambiguous experimental signal that help us to uniquely determine the Compton form factors. And in the case of this proposal on unpolarized proton, it is a real part of the Compton form factor H. And to conclude, the direct access to the real part of the interference amplitude via positron beam will no doubt constitute a major step forward for DVCS studies. Thank you. Yes?
I think I forgot to unmute. The first reader of this proposal is Elke Aschenauer, and she will now have time for asking questions. Please, Elke.
Hi, Eric. Thank you for the nice presentation. I have a couple of questions. And what I would like to go to first.
Can you hear me?
Yeah.
Yeah.
Yes. Can you hear me?
Yes, I do.
Okay, good. So then I continue on. Because there were kind of issues with seeing, for example, your slides were always behind for what you were talking. But okay, let us go to, not a problem. It's probably a network issue. Let us go to your predictions with impact studies you had on slide 12, I think it was.
We seem to
if
be
I'm
missing.
correct.
Yeah.
Elke, is that correct? Elke is online. I don't hear you.
Elke is online and I hear her.
Yes, I also hear her.
I also hear. So Marcus, it's no problem.
Yes, please.
So,
maybe. Yeah.
Can we go to slide 12? So I can ask.
I'm there. Do you see? Do you see?
Okay. I don't see this. Okay. I ask my. As I say, it is extremely. The connection is very tricky. So first of all, one thing which I wanted to ask: the models you have used to study your impact.
Yes.
Are they reproducing these beam spin asymmetries which have been measured at HERA?
This is I'm not sure of that. This is the model. Well, in fact, we have been using in the proposal 4 different models, and
I know.
the one we show this is Kinematic from 2015. I'm not sure with respect to error. I'm not sure.
Okay, would be good to clarify this. But then
Okay.
you have used your pseudo data. You impact them and you do with and without electrons, and you get kind of a reduction. But have all the other, as you already also discussed, there's a large DVCS program going on at JLab. Have all other data which will be accumulated before you will be running integrated in this study as well, or is it only an impact study of your experiment?
It's the impact study so we are taking into account the data coming out from run group A, and also the longitudinally polarized target. The only data that we have not been considering is the polarized transverse target. But
that's excellent. That's very good. Very good. No, that is exactly what I was hoping for. Okay, thank you. That is.
Can I comment just that? So these data don't exist yet, right? So he is anticipating statistics. Yeah.
Understood. So you take the anticipated pseudo data which have been and sees, and what is the impact of your experiment on top of this? No,
yes.
Understood. That is perfect and all perfect. I just wanted to make sure that I understood correct. So that's nice. So now on the question of measuring, you suggest to measuring with electrons and with positrons.
Yes.
Because you want to cancel systematics, so you want to have the same beam conditions. Do you have a feeling how much bigger systematics would become if you would use the electron data which are already existing? If you were measuring with positrons, how that will impact your systematic if you take...
At this time, that will much more impact the statistics, because the existing data in the configuration, you need to have the configuration of outbanding to the comparison. For the systematics, it will just, you will have to consider in addition that changes on the target, so there will be some additional effect due to the target length, and also possibly due to the way we are dealing with the background. And so the effect on the systematics will be larger. I don't know how much, but it will be larger.
Okay. And the last question I have has to do with higher twist, NLO effect, and target mass corrections, because you measured very high X and low Q square. So higher twist is probably not to be neglected, and it can be different for the electron and the positron data because you probe real and imaginary part and things like this. So how, and in all the studies which have been done, they have been, it's leading twist, and so some higher twist effects have been neglected. Do we have a feeling and understanding from earlier data, maybe even the 6GV data, how big these effects are and how they can actually impact the interpretation of the data?
So maybe this question I could give it to Carlos, because he was doing the experiment, and where they see that you have ambiguities in order to do the separation between the interference and DVCS contribution when you are not using positrons, and those ambiguities are due to higher twist effects and next to leading order effect. So maybe if Carlos wants to say something on that,
I will discuss it during my presentation, so maybe we can come back to it later.
Okay, as I can ask a question at that moment. I'm happy to wait. Okay, I'm satisfied at the moment, Markus.
And maybe just to say that in fact, with this neutral beam spin asymmetry, which is connected to the DVCS field, we might have a flavor of what is the effect of higher twist.
Okay.
Thank you very much, and sorry for the mess I apparently created. I had lost connection and could speak but not hear anything. The second reader of this proposal is Feng Yuan. Feng, do you have any questions you would like to ask?
Actually, my questions kind of overlap with what Eric had, but since you are on this slide, I actually have the more slightly different question than what Eric asked. So you say that the neutral beam spin asymmetry will be sensitive to higher trace effects.
Yes.
My feeling is that it's every observable in this kinematic will be sensitive to high trace effects, right?
Okay. Yes, you're right, but you should be able to see it more clearly in this observable. But of course, all these observables can have contributions from higher twist.
All right. So I just want to make sure. So, let me see. This has been discussed during your answer to Erica's questions. So in the page 12, you mentioned about systematics. I was confused when you talk about it. It's where the systematic uncertainty will be reduced.
So the systematic uncertainty. Yeah, so maybe I should go in full mode. Is where you need to compare the position of the red and blue points with respect to the black line. So the black lines represent the model values that has been used to generate the observables, and the blue points are when you extract the real part of the Compton form factor H without considering positron observables, and the red point when you consider those positron observable. So you see that you have you tend to have a kind of systematic shift of the blue points with respect to the model value, while when you have the red points, you get much closer to the model values that you have been using. So that's this kind of systematical effect I was talking about.
Okay, just to clarify, you answer Echo's questions that for this simulation, use the electron.
I use, yes, electron data, which electron data to come, and positron data that we are asking for today.
Or including also your proposal with electron.
Yes. The blue points are considering only the electron data, and the red points are considering these electrons plus the positron data.
I know the electron data is the existing data plus future data, but not included in your proposal. Is that right?
The electron data are the data to come. They are not yet existing, but they have been approved by previous.
I understand. My question is that does that electron data include your proposal data? Because you also propose to have electron beam, right?
Yes. No. There is only a small part of run group A data that we can use in order to do the beam charge asymmetries. And maybe in the answers we were giving to the TAC committee, we evaluate that it is less than 25%. So that would be a big impact on the statistic to compare only with this data. I have been clear.
I'm not so sure. It's a simple question. So electron data you have does include your proposal electron data or not?
No.
Okay.
No.
Okay.
Very good. Is there any other question from the PAC? That does not seem to be the case. Then maybe I can have an add-on question to the answer you gave to Elke's question regarding the importance of electron data. You point out that you need electron data with the other setting of the class 12 spectrometer.
Yes.
And for the purpose of statistics, would that data also be taken with the regular CBAF electron beam rather than the secondary electron beam that you are proposing?
These are the data from run group A and taken with the regular positron beam. Oh, sorry, regular CBAF beam, electron beam.
No, sorry, I'm asking about the electron data you argue that you need for your measurement. And you clarified that you need these with the other polarity of the spectrometer, so you cannot use existing or already approved future data.
No, we cannot use. We can use only a part of
Yes.
data that has been
for
collected.
the remaining part that you would still need, could that also be taken with a regular CBAF electron beam rather than with a secondary beam that you are mentioning?
We would prefer to take that with the secondary electron beam to minimize the systematics effect.
Yes, I understand. But the question is, how much, let me rephrase the question, how much do you think you would lose if that had to be taken with the regular CBAF electron beam? Please, Volker.
Yes, so I mean, the regular beam is of high quality, right? Whereas and it has a very small spot size at the target, as you probably know. Now, with this beam, it has a much bigger emittance function, and so the beam spot size is a factor of 3 or so larger, possibly more, and it will have a wider tail. So that is and this may affect in particular sort of if you compare such a beam quality, which is poorer but still good, with the perfect beam quality. I think we are afraid that the systematic errors would be significantly higher than if you just compare the data taken for electron with the same quality as the data taken with a positron beam. They come from the same source. That's a proposal.
Okay, thank you very much.
Really existing data on the outbending that we need are taken with a regular, as Eric said, and but sort of the control of the systematic, of course, was not pay attention to the issue that we will be facing when we do the positron run, if it gets approved.
Okay. If there's no other question, I suggest that we move on to the next proposal presentation. This will be given by Carlos Munoz Camacho, and that is on a DVCS measurement with positrons in Hall C. Please, Carlos.
Yes, good morning, good afternoon, everyone. If you allow me, I will switch off my video now, just to avoid any lag with the internet connection. And I will go ahead. So I'm going to present a proposal to measure DVCS cross-sections using a positron beam in Hall C. This is part of the same scientific program that Eric just presented. This experiment would use the new neutral particle spectrometer, NPS, Hall C, and is supported by the NPS collaboration. I would skip most of the introduction and motivation on DVCS that was already presented in the previous talk. Let me just remind you here for completion in one slide the key of the measurement that we are proposing. So deeply virtual Compton scattering, DVCS, is the cleanest channel to access GPDs of the nucleon. The theoretical framework is very solid. The leading twist all-order QCD factorization theorems have been established. Therefore, GPDs are process-independent, universal quantities that contain essential information about the dynamics of the partons and allow to make predictions involving nucleons at high momentum transfer. DVCS is even more interesting because it interferes with the well-known Bethe-Heitler process. that allows not only to measure the DVCS cross-section, its squared amplitude, but also the interference with the beta-Hyler amplitude. And this is quite unique, as we can measure the DVCS complex amplitude itself, and using a polarized electron beam, even independently access the real and imaginary parts of it. In order to independently measure the interference term and the DVCS square term, we can use the fact that the beta-Hyler amplitude is charge even, but the DVCS amplitude changes sign with the charge of the lepton. And this is the only clean and model-independent way to access this piece of the cross-section. GPDs appear in the DVCS amplitude as convolution integrals, which are called quantum form factors, or CFFs. And through the real part of the amplitude, we access the principal value integral. And through the imaginary part, we can measure the GPD itself, but along one particular kinematic line, x equals psi. The DVCS program at JLab has been developed with a complementary approach built on particular capabilities of different experimental holes. On one hand, there is the wide program of measurements proposed to be performed with large acceptance detectors, class, and more recently, class 12, where observables are surveyed over a wide range of kinematics, but with limited statistical and systematic uncertainties. And this is the part of the program where the previous proposal you heard about would fit. On the other hand, a parallel program of precision measurements is carried out in high resolution but limited acceptance holes, like hole A and hole C. Here we investigate the details of the reaction mechanism, the dominance of leading twist, the size of higher order corrections. We can perform LT separations for meson production channels, and so on. And it is within this high precision program that this proposal would contribute. We've been developing this program for the last 15 years at JLab, and I list here a few highlights to illustrate some of the key results obtained. First of all, DVCS was observed to be dominated by leading twist amplitude, where the virtual photon scatters off a single quark of the nucleon at relatively low values of Q-square, of around 2 GeV square. It was also shown that it has sizable amplitude and is not dominated by the beta-Hyler process as was initially thought. Now, this being said, a second round of precision measurements evidenced the necessity to include power corrections of the order of T over Q square and target mass corrections in order to fully describe the azimuthal dependence of the cross-section. We have also used the beam energy dependence of the DVCS cross-section as an initial way to separate the DVCS squared and the interference term of the cross-section, which is the goal of this proposal also, but I will show in a minute that that procedure has some limitations. And finally, we have combined DVCS with proton and deuteron targets in order to flavor separate the quantum form factors of the nucleon and also measure pseudoscalar meson productions by zero in particular, which could give us access to transversity GPDs of the nucleon, so with both proton and deuteron target. Now, one way to separate the interference term from the DVCS square contribution, so let's see, missing one slide, I think. And one way to separate the interference term from the DVCS square contribution in the absence of a positron beam is to exploit the difference beam energy dependence of each of the terms in what we have called a Rosenbluth-like separation. The interference term goes as a power of 3 with the beam energy, whereas the DVCS square goes as a power of 2. And of course, at fixed Q squared X and T, the level arm in beam energy is limited, but nonetheless, combined with the phi dependence of the cross-section, we can in principle separate the different contributions. And here are the cross-sections we measured at constant Q square, X, and T, but two different beam energies, 4.5 and 5.6 GeV, and as a function of the angle phi between the leptonic and hadronic planes. One of the things we noticed is that if we try to perform a leading twist leading order fit of the azimuthal dependence of the cross-section, the fit does not reproduce the shape of the measurement. In order to perform this fit, we used the quantum form factors defined in the frame where the light cone axis is in the plane formed by the virtual and real photons, and consider only the helicity conserving quantum form factors in the fit. This is the frame where the power corrections such as finite mass corrections and where target mass corrections, were implemented by Brown and collaborators. Now, if we include helicity flip quantum form factors, then the fit reproduces quite well the data. And we tried two different fits that actually overlap in the blue curve here. One fit includes quantum form factors that flip the helicity of the quark by 1 unit, and these have the same Q-square dependence of higher twist quantum form factors, and we refer to that as higher twist fit. And the other fit is made by including quantum form factors that flip the helicity by 2 units, which have a Q-square dependence equivalent to that of next to leading order corrections, and we refer to that as NLO fits, NLO CFFs. So both fits reproduce the data well, but they're indistinguishable. We can describe the data with either set of them. So what we did to separate the interference from the DVCS squared terms under these two scenarios, we tried both. Right? First, one where we include helicity flip quantum form factors in blue, and one separation including instead double helicity flip quantum form factors in magenta. And you see there are significant differences according to which scenario we choose, especially in the right plot, which shows the helicity-dependent observables, where the DVCS squared term is 0 in the double helicity flip scenario, but has a significantly large amplitude in the single helicity flip assumption. So this illustrates what can be done and what we did in the absence of a positron beam in order to separate the DVCS squared from the interference in the DVCS cross-section. Now things are much cleaner if a positron beam is available. As I mentioned at the beginning, a simple subtraction of the cross-section obtained with electrons and positrons gives you twice the interference term, and the sum of them twice the DVCS squared term, plus twice the beta Heitler that we can easily subtract. So we can properly separate the terms without any assumption. In addition, we can continue to benefit from the different energy dependence of the various contributions. Since the relationship between the cross-section and the different quantum form factors is very involved, we should use any kinematic dependence at our disposal to further constrain the extraction of GPD's data. So we propose to run the same kinematics of the already approved experiment E12-1310, but using a positron beam. You can see in this plot the kinematic coverage of the different settings in the Q-square X-plane, which includes settings at constant X and several values of Q-square and different beam energy. In our projection and impact plots that we included in the proposal, we have assumed 5 microamps of positron beam. Of course, the experimental equipment can easily handle a higher beam current. So if a higher beam current is available, higher statistics would be collected. Also, to be conservative, we have assumed that the positron beam will not be polarized at high current. With these assumptions and 77 days of beam, we would be able to collect about 25% of the statistics already approved with an electron beam. Now, Eric already covered the current plan for a positron source and some simulations of the transport of the positron beam in CFFS, so I will not discuss it here again. Maybe just one point to repeat is that the positron beam emittance is certainly higher than for an electron beam. At high beam energy, this only implies a factor of 2 in beam size, but before in the machine, the emittance would certainly need to be reduced to make this possible. Let us, however, acknowledge that the implementation of a multi-hole high current polarized positron beam at CFFS is complex. and a list of the main challenges is available in the TAC report. However, if the PAC finds our physics program compelling, our collaboration is ready and eager to engage with the lab to investigate its feasibility. So I quote here the conclusion of the TAC report, which states that while a positron beam upgrade is a major upgrade, a multi-hole positron beam capability could be of great potential for a future JLab 12GF science program. The experiment would run in hole C and take advantage of the upcoming neutron particle spectrometer facility, NPS. NPS is a combination of a high-resolution lead tungsten calorimeter and a sweeping magnet that enables to run at very high luminosities with levels of background under control. The improvement on the recoil proton missing mass resolution by using a lead tungsten calorimeter compared to lead fluoride calorimeter that we have used up to now is illustrated in this plot, where we can see an improvement of around a factor of 2. Here are the projected results on 3 different Q-square X settings from top to bottom and 5 beams in D from left to right. The red points show the projected results for a positron beam, and in magenta for an electron beam. This allowed to very cleanly separate the DVCS square term in dark blue and the interference term in green. The bars around the points show the statistical uncertainty, and the blue band at the top of each panel shows the systematic uncertainty. Let me in more detail list the sources of systematic uncertainties, which is something which was not done in the proposal document. The reason was that we expect the same uncertainties as for the approved electron experiment, which I show here now. The positron beam itself, once it is transported to the hole, should have, according to simulations, a similar energy spread as the current electron beam and not only a slightly larger size. That is something that the experiment should easily live with and should not create additional uncertainty. Now, based on our knowledge of the experimental setup and our experience of previous DVCS experiments, the main systematics are listed here. One of them is the exclusivity cut in the missing mass distribution, which is about 2%, and the knowledge of radiative corrections that we also estimate to be about 2%. So overall, about a 4% systematic uncertainty is projected for these measurements. Additionally, the measurement of pi-zero electroproduction cross-section concurrently with DVCS would allow to monitor the relative systematics of the electron and positron runs. Now, to evaluate the impact of positron data on the extraction of GPDs and the associated Compton form factors, we have performed a combined fit of the projected proved electron DVCS measurements only, and then with the inclusion of the proposed positron measurements. For the electron data, we include both helicity-dependent and helicity-independent cross-section measurements. And for positrons, we only consider, of course, the unpolarized cross-section measurement. We have included in the fit Compton form factors associated to GPD H and H tilde, but we have neglected GPD E tilde, which is highly suppressed, and GPD E, where we would need a polarized target to have sensitivity to it. However, we have included all orders of CFFs, helicity-conserving CFFs, and single and double helicity flip CFFs. So a total of 12 parameters, including their real and imaginary parts.
You have 5 minutes left.
Okay, thank you, Marcus. And then we have used all the physical dependencies of the cross-section at our disposal: the angle phi, the beam energy, the Q-square dependence of the cross-section, the helicity of the beam for the case of the electron data, and we compare to the case where, in addition, we include the beam charge dependence of the cross-section. So this plot summarizes the results, where we see one row for each of the quantum form factors, the real part of H, the imaginary part of H, the real part of H tilde, and the imaginary part of H tilde. The first column shows the helicity conserving CFFs, and the second and third column, the helicity flip CFFs. And you can see the uncertainty obtained with electrons only, or by combining both electrons and positrons. And then the ratio of the size of the uncertainties is given in the last column of the plot. So we can observe that the addition of positrons improves the uncertainty by about a factor of 6 for the real part of H, and a factor of 3 to 6 for the real part of H tilde. In the case of the helicity conserving CFFs, even the helicity flip CFFs are extracted with smaller uncertainties, with roughly a factor of 2 improvement. Now, the imaginary part, of course, shows less improvement, but this is simply because we are not including any polarization data in the case of a positron beam. Now, one thing to realize is that the uncertainties of this extraction are dominated by the correlations in the different fit parameters. The DVCS cross-section has a complex dependence on all of these quantum form factors, and the extraction is sensitive to their correlations. And it is indeed the inclusion of positron data that allows to reduce these correlations. This is illustrated by the covariant matrix of the fit, where you can see the one-to-one correlation coefficients between each pair of parameters. In particular, you can see that in the case of electrons only, and the real part of the helicity conserving CFFs H and H tilde are correlated almost 100%, 94% actually, whereas the correlation is reduced to less than 40% if positron and electron data are combined. So this brings me to my conclusion. A positron beam is the unique and only way to unambiguously separate DVCS2 from the beta-High-low interference term. They will have a strong impact on quantum form factors fits and extraction of GPDs, and overall in the nuclear imaging program, which is one of the core missions of the Jefferson Lab upgrade. We request 77 days of positron beam, assuming a beam current of 5 microamps or higher if available. And we will use the same setup in Hall C as the already approved experiment E12-1310, and the same kinematic settings in order to combine electron and positron data. Thank you very much.
Thank you very much, Carlos, for your presentation. We now start with the first reader of this proposal, who is Feng Yuan. Please, Feng.
Carlos, thank you very much for the clear and nice presentation. My first question, actually all the questions relate to the high trace effects. So you mentioned in the proposal, also in your presentation, you say added positron beam would help to understand high trace effects. So the reason is that just add additional more data, or there's additional reason for that?
It's mostly the addition of more data which have different dependencies, right? Okay. So the only way to understand the Q-score, the higher twist effects, is to measure Q-score dependence of observables, right? That's the only thing that QCD can tell us is the Q-score dependence. So by comparing the Q-score dependence of each observable, that's the strategy we are developing. So that's why every time we measure the cross section, we choose settings that at fixed X, we have at least 2 or 3 points in Q-square. And then we add the energy dependence, and now we add the beam charge dependence. But yes, it's simply because we have more data which have likely different kinematic dependence in the cross section.
Okay, so thank you. Can you back to page 16 again? Yeah. So in your fit, do you mentioned about this as a leading trace fit, right? for the impact?
No, we fit the cross sections using all these Compton form factors. So the helicity dependent, the helicity conserving Compton form factors and the helicity flip. So they're all included there. But we don't have a fully higher twist parameterization of calculation of the cross section.
Okay.
As you know, the DVCS. Yeah, go ahead.
So the comment there is factor 2 for high HT is represent a higher twist.
Yeah, so higher twist. What we mean by higher twist there is Compton form factors that flip the helicity by 1 unit. So the Q-square dependence of these Compton form factors is the same Q-square dependence of higher twist effect. They are suppressed by 1 over Q with respect to the helicity conserving Compton form factors.
Okay. This is just for particular observable, if I got it right, right?
Right.
Okay, another curious question. So compared to the previous one, OB presentation, for example, for your upper right plot, they have very interesting behavior for the systematic reduction as function of T. You seems not observe that, right?
What do you mean systematic reduction?
So if I remember correctly, in their case that if T goes to right direction, that means it goes to more positive, the reduction is bigger. For the more negative T, actually, is smaller.
Yeah. Yes. You're right. That might be just a small effect on the model. So we see for H, we see something which is flat here on the top black curve. Mm-hmm. But for H tilde, for example, there is also a T dependence of the reduction in the error bar. So I'm not sure there is a lot of physics in there, but might be just an artifact of the model. Yeah, a model dependent. Yes, I don't think there is a lot to extract from that dependence. It seems to vary with the GPD, and I think so. For the previous results only had GPD H in the fit. Here we have 2, so maybe there is a compensation somehow. I don't know.
Okay, thank you. Max, I'm done with my question.
Thank you, Feng. Then I call on the second reader for the proposal, and that is Elke again.
Yeah, thank you, Carlos, for the nice talk. I have a couple of questions. So I tried actually to find in the proposals the numbers of the resolution of the crystals, the term which goes with square root E and the constant term. Can you provide this? I couldn't find it.
Well, we haven't measured it. So this is a new calorimeter, as you know, we are building. So our estimate.
Yeah, but you must have been.
Yeah, sorry. Yeah. Yes. So our estimate is 2% over square root of S. Sorry, square root of E, and a constant term of 1%. That is our estimate according to
standard, which is assumed for lead tungsten. Okay.
Right.
The next one, you're right on the slide number 16. So I understand that you took into account your own electron data, own meaning the ones which will be measured at hole C, and then you put in the positron data. Of course, a true extraction of GPDs we know is the same as for collinear PDFs. You will take the world data and you do a fit, and then you kind of constrain your GPDs, because with one experiment you hardly can do this. So now I think this impact which you show here is of course overestimated, because there will be a lot of other data available. So I think if impact studies are done, it would be important to really take into account all the data you expect to be available, of course, always with a caveat. If they are not yet taken, you don't know all the statistical and systematic things which are available before you take the data, and then you study the impact. So that basically is the same way as we do for EIC. I feel that is gives a proper representation of what the impact of an experiment will be. And it would be nice if this could be done for this experiment as well, because there will be other kind of experiments measured long before that a positron beam will be available.
No, I agree that would be better to do that. The only thing is that you need to fix some kind of parameterization, right? You need to take a model to combine different kinematic settings. So no, I agree that's the way to go. What we wanted to do here is to estimate the impact by doing kind of a local fit, kinematic by kinematic. In the long term, I agree with you.
Yeah. Okay, I have also a point to the Q-square dependence. If you can go back to your kinematics plots. And that is maybe also something, where you show yes, this one, thank you very much. And that is maybe also something for the theorist in some way. So you basically span a Q-square from, let's say, 2 to 6, and actually at a fixed x, it's smaller. Q-square dependencies also for the GPDs go with a logarithm. So your Q-square bandwidth is actually very small. So and that is maybe more to theorists, I really have a hard time that with this small Q-square span, you can really kind of separate NLO effects and higher twist and all of this type of things. So there needs to be some method established or some theory or something to really kind of get a better handle on it, because if not, I don't know how you will ever kind of get a handle on this kind of things. Do you have some thoughts on what to do to kind of improve this?
Well, you see the kinematics are limited, right? So you can see the shaded band is the resonance region, and then the line there is the beam energy. So we are covering at every x, we are covering the maximum we can, which is about a factor of 2 to 3 depending on the x. But then there was a higher point at Q-square around 8 that we could do, but then the PAC considered it too time consuming and it was not accepted. But that's all we can do. The other thing we can do is to make precision measurements, and that's what we're proposing. Instead of increasing the level arm by a huge factor, which we cannot, we can reduce we can increase the precision. And then by looking at the small effects over a smaller Q-square, we can try to shed some light on it. But that's all I can tell you now.
Good. Can I ask a question maybe to both experiments, which has to do with the beam development of the positron beam? It's clear that is a large investment, and it's also until you, at the moment, I think it's fair to say there's a conceptual design of how positron beams at Jefferson Lab could exist. And there were, for example, for the Hall B, and you also discussed that the emittance of the beam is bigger and so on. So do you have actually requirements of how the beam parameters have to be that you can kind of measure with the existing setups, so that you don't, for example, have to increase and modify also the beam lines in the halls, or you have not looked yet into this so that you don't have a lot of scraping on the beam lines and things like this? Has that happened?
Maybe I can let one of my colleagues, Joe, you want to take that? If I think he's
sure. Can you hear me okay?
Yes.
Yes.
Yeah. So you're correct that the development is like a non-trivial effort. Most of the work has been involved with the source work to understand what the beam production would look like. There's been some effort, although I'd say a smaller effort associated with the requirements through the machine for the positrons. So far, we've been using the electron performance of CBAF and requirements at some fixed points leaving our injector. And so those are consistent with what Eric and Carlos have been showing in their slides. So ultimately, as Carlos pointed out, there needs to be more work done and understanding what the real requirements would be, what are the constraints and limitations that we'll need to have. And fundamentally, that's addressed. We're confident we can address whatever requirements are there, but we'll need to refine those to understand how to optimize the performance of the source, and then what limitations there might be on the yield. I think fundamentally that's the bottom line. We can always reduce the yield to improve the beam performance in the accelerator and at the experimental hall, but we need to look in more detail on the best way to optimize that yield. I think that's the main problem ahead of us.
Okay, thank you very much.
Sure.
If I could add a comment, Larry Cardman here. If you can hear me?
Yes, please.
So I would note that there has been some very useful and valuable work done on the source by the PEPO experiment, and some, let me call them, sketches of potential performance versus beam parameters. There is an LDRD proposal by the source group to develop that into something that would be substantively more quantitative and precise for the kinds of parameters that are necessary for the beams discussed here. And I would urge you to encourage that so one can follow through on the physics promise of these beams.
Thank you very much. If there
no
is
more questions, Marcus.
Yes, please. Yeah.
No more questions. I'm fine.
No
Thank
questions.
you.
In that case, let's thank our speaker and move to the next presentation. The last presentation for today, that's by Bill Lee, who will present a proposal on backward angle exclusive pi-0 production. Please, go ahead.
Thank you, Marcos. Can you hear me okay?
We hear you all right.
All right. Okay, so can you see my shared screen?
We can see that all right. You are set to go.
Thank you very much. I will turn off my camera for the benefit of the bandwidth, and let's get started. Thank you. And hello, everybody. My name is William Lee. I'm from College William Mary. Today, I'm presenting our proposal on the backward angle exclusive pi-0 production above the resonance region. It is my pleasure to introduce Justin Stevens and Garth Huber as co-spokesperson on the proposal. And we have a list of very enthusiastic collaborators on this new opportunities. So this is today's outline, including a very short introduction to the U-channel physics, and I will touch base on our 4 experimental objectives, and then some technical detail about the experiment. To start with my introduction, I would like to go back to the Rutherford scattering. Recall we have the alpha particle being shot at the gold atom. And there are forward scattered alpha particles, and there are also back recoiled alpha particles. Through the forward scattered alpha particles, we learned that the transverse structure of atom, and also from the backward scattered alpha particles, we learned these structures within the gold atom are very, very point-like or very hard. So the point here is that we really have to combine the forward and the backward angle observables to reveal a full structure of the atom. So in the probing of the proton structure case, we have an analogy very similar to this. We have a photon that is being used to probe the proton structure. As you can see on the bottom, I'm using an example from Michel Guedel's thesis, and this is the pi plus photon production. As you can see in the forward angle, the low T, we have the T channel Reggie exchange diagram give rise to the forward angle peak at low T, and at very high T or low U case in the backward angle regime, we also have the baryon exchange diagram that contributes to this rising in the backward angle scenario. And this is a typical example of bringing the forward and the backward angle observables together to reveal the full structure of a proton, going from the soft structure in the forward angle, then the hard structure in the middle, and then the soft structure again in the backward angle. So in Jefferson Lab, the electron production case, we have normally 4 parameters to see the evolution of the nucleon structure. We have the X, that is interacted parton momentum fraction, normally is just being defined by the available beam energy. We also have the W, that is the square root of a Mandelstam variable S, that dictates if a process, whether it's in the resonance region or not. Or we also have the Q squared, that transit approximately related to the wavelengths of the virtual photon probe, and that can be seen as the resolving power of our interaction. And then we also have the Mandelstam variable T, that is can be linked to, inversely proportional to the impact parameter B. So if we really want to probe deep into the nucleon, then we just go high in Q square and go high in T. Then we bring down the impact parameter, then we probe hard into the nucleon. Notice that this is only the forward angle approach. Mandelstam variable U is missing from this interpretation, and our significance of our measurement is to really search for the significance of the U evolution in terms of the nucleon structure. So here on this slide, I have an example side by side showing you how do we probe into this U channel structure. So I'm using the pion form factor experiment from 6GeV as an example. In this experiment, electron coming in interact with the liquid hydrogen target. The electron scatters into one of the spectrometers, and the produced pi plus, this is the T-channel pi plus that is produced the forward angle and leaving the neutron behind. And then in the constant time peak, you can see these events very, very distinctively. In the same time, in the same setting, the electron coming in scatter into one of the spectrometer, and then we have a proton is produced in the same time. And then after our analysis, we found, oh, there is omega that is actually produced in the backward angle. Notice that this omega goes backward angle in the center of mass frame. And these events are showing as this little peak on the constant time structure. So this is what my thesis work is on, to analyze this U-channel processes. And notice that one thing I would like to point out is that W here is larger than 2, so that we know that these omegas are not coming from any nucleon resonances. In order to understand these omegas that is produced in the U-channel kinematics, or at very large T, we have to borrow something very similar to GPD, as we know that the GPD is like the hadron tomography of a proton, but it's normally just predominantly studied and extracted using the forward angle observables. And as we know that all GPD models kind of fails in description of cross sections at a large T, and we really have a maximum T in our case. So here we have to borrow something related to GPD. It's GPD-like, and is known as the meson to nucleon transition distribution amplitude. And this universal structure will turn a target proton into a final state final state meson, and the 3 valence quark will leave this generalized structure and then interact with the virtual photon probe and hydronize into a fast nucleon in the forward direction. This backward angle factorization scheme, or known as the TDA, so far has generated two testable qualitative predictions that can be tested through experiment. First is that the separated cross-section sigma t will scale as 1/8 q squared to the power 8 scaling behavior. This is kind of very classic for any scaling behavior. And then we also have it predicts the transverse cross-section will dominate longitudinal. So the validation of these quantitative predictions come from separately 6 GeV measurement at Jefferson Lab. First, we have the Halsey omega production from my thesis. As you can see that the L2T's cross-section ratio at even q squared of 2.2 is approaching 0, indicating that the sigma t is actually dominating L. And the scaling evidence come from the class 6 pi plus production. As you can see that above q squared of 2, the total cross-section scales approximately being described by the band that is the TDA prediction. These initial evidence has given us enough courage to develop a 3-phase validating plan to systematically study the TDA at the 12 GeV Jefferson Lab. So we have 4 objectives to our measurement, as I introduced. The first 2 objectives are concentrating on searching for the U-channel peaks for all mesons, and then we'll be moving on to the next stage, which is our objectives 3 and 4, that is to validate the TDA predictions. So I'll be introducing these objectives in the next few slides. Objective number 1, we would like to demonstrate the existence of the U-channel peaks in the exclusive backward pi 0 production. We have selected the pi 0 because there is a relatively large, it's a relatively clean channel and have a very large community interest. As an example, the MPS experiment as presented in the previous talk is looking at the small T channel peak, and we have selected in this proposal the matching kinematics. We will be able to produce the U channel peak at the T max. So together, bringing together the forward and the backward angle peak, then we will be forming this kind of plot showing on the same T axis both the forward and the backward angle peak, like I did for the omega case. Then I will move on to the objective number 2, which is to look at the U dependency. We'll be performing the classic phenomenological studies that one typically do with the low T channel studies, as you will extract this parameter B, which will be directly translate to the interaction, the minimal interaction radius, and to see how the radius will change as a function of q squared. That is a leading observation to see how proton structure transition from hadronic to the partonic degree of freedom. And this is a common study that one do for the T channel physics. Objective number 3 will be directly challenging the TDA predictions of the dominance of the transverse cross sections. As you can see, our projected T to L ratio at 2, 3, 4, and 5 q squared, and we will be concluding the dominance of T if this ratio is above 10 at a q squared of 5. So as you can see, our expectation is that for this ratio to arrive at around larger than 100. So last, we'll be looking at the prediction number 2 from the TDA, which is the transverse cross-section scale as 1 over q to the power 8. So as I have plotted our expected data and our expected error bar. So I want to mention that the experimental beam time that is in this proposal is determined aiming at extracting the n factor to be with the 4 plus minus 0.25. So this is our experimental kinematics table. As you can see that between q squared of 2 and the q squared of 5, we'll be performing the standard LT separated cross-section, and we'll be taking additional data at the q squared of 2 and the w of 3. So we will get the W scaling studies. And then at the q squared of 6.25, we will be taking additional setting without LT separated cross-section to do the q squared studies on this point. As you can see that we will be having a proton in one arm and an electron in the other arm, and perform the missing mass reconstruction technique for the pi0. Here I want to point out some of the positive things that from the theory TAC report, as in the eye of JPAC, they acknowledge that our measurement will verify how hard scattering interaction play a role in the backward exclusive production. However, if we cannot demonstrate, even if we cannot demonstrate the hard scattering is relevant in such kinematics, our data is still very valuable in studying a soft, non-perturbative interactions. Either way, our measurement will inspire more theoretical and experimental activities. So this is a very strong endorsement from JPAC. Let's moving on to the experimental technicalities. So we have the particle identification. So we normally, for most of the settings, we just have the HMS detecting the electron and the super HMS detecting the proton. And we're using the standard PID package for both spectrometers. And I have listed various of settings that to be put in for various of detectors to help us identify these particles. So thanks to our choice of a momentum setting, so one of the primary PID is the beta versus the constant timing structure. That, as you can see, I put a example from already ran a K-on LT separation experiment at hole C. Even without any acceptance or PID cuts, we can kind of clearly see not from the mean bunch, but a little bit from the side bunch, that there is a kind of a separation between the two, between the forward or the T channel meson production and the U channel meson production process.
You have 5 minutes left.
Thank you very much. And also we have our primary background. So as you can see, our pi0 peak is here, and we have the DVCS, which is very low in cross-section. And we also have the 2 pion exchange phase space that's contributing only one side to our pi0 peak. So we'll have a very easy time to do the PID and reject the background. So the requirement is that we request 29.4 days of beam. And all of these are standard tune beam that at the time of running. And we will be happy with the polarization that be available. So yeah, so here I have listed a few technical refurbishment item, which one of them is already planned, and we would like to have HMS aerogel to be aerogel PMT to be replaced for our measurement. And then here I want to address one of the comments from the experimental TAC report is that they commented our lowest angle setting for some of our measurements. But I want to just assure PAC that we did not go out of our way to ask for something that is not part of the spec. As you can see that I have listed the design spec in the brackets, and what we're asking for is within that spec. However, we do acknowledge that realistically, we may not reach this level, but the same requirement has been made by other experiments, such as the pion FI12 measurement in Hall C, which will be running next year. So we only ask to work closely with Hall C and the pion form factor experiment to see what is the minimal achievable angle, and then we will retune our kinematics to the minimal achievable angles. So here's our beam time request and how 29.4 days breaking up. We have estimated, we have included 10% of the dummy target running, and all of the liquid hydrogen running will be 70 microamp. So we have considered all of the overhead, including the changing configuration, etc. So, and at last, I would like to bring to PAC's attention, also the attention of the interested party, is that we are hosting a workshop in discussing these new opportunities, the backward or the U-channel physics, that will be hosted in September. So we plan to sit with the interested party together to develop a plan that is to move the backward angle forward for 12 GeV Jefferson Lab and potentially to the EIC. Thank you very much. This is end of my presentation.
Thank you very much. So we have now time for questions. I call on the first reader of this proposal, and that is Steve Dittman. Please, Steve.
Still Deitman. Thank you for bringing up the issue of the TAC brought up with the angles. Does that change any of your beam time if you have to run at the angles that are somewhat larger?
In short, no, it does not.
Does it change your ability to measure physics that you want to measure?
In short, no, it does not.
Thanks for the short.
So if you wanted me to elaborate that a little more, I could.
No, that's good. That's what I expected you to say, because it's very broad stuff you're looking at. So I would imagine that it wouldn't matter much. Just your ability to get the pi naught exactly backward from the proton would be the only issue. Your count rate calculations, what theory was that based on?
Which slide are you talking about? The like these predicted cross sections?
Yeah. For example, what were your beam time estimates? Which calculation was it based on? A TDA calculation or another calculation, for example?
Okay. So here is that because one have to realize that there is currently no reliable model in the kinematics that we're trying to measure. So we have consulted with the theory experts from JLab, JPAC. We call it the vice approach. Let's put it that way. So we have taken the well-known forward angle cross sections and changed the T dependence for the U dependency and scaled the cross section by the factor of 10. So that's the best approach. Let's put it out.
On a TDA model?
It's comparable to the TDA model, but I would like to say that the TDA model did not make a specific predictions at the kinematics we're trying to measure.
I was wondering why it wasn't in your proposal. Okay.
Yeah. So we basically took a phenomenological approach based on the data, based on the experience, to come up with a model to estimate these.
Okay, well, here's my real question.
It's Garth here. If I could just add a quick clarification. So just to elaborate a little more on what Bill said, we've used the estimates that were used for the forward angle T-channel pi-0 experiment, and then we applied the approach that Bill explained to convert them from forward angle to backward angle.
Thank you. But just to give an arbitrary number, what if the cross section is half as big as you think it is? What happens to your results?
as in for example this plot.
Yeah. Say it's half as big as what you have there. How does that change your use of the beam time?
So if the cross section is so let me address this. So we have let's say if the cross section is half as so it's basically it will change our statistics by a factor of 2. Then we kind of take the square root of whatever that is remaining. For example, we plan to have 10,000 events or 1,000 events. Then we basically reduce that by a factor of 2. Then we take the square root. So it will hurt us in, let's say, in a percent level in the systematic error. So it will not hurt us significantly. So we will change at best. This number here will be changed from, let's say, 0.4 plus minus 0.25 to 4 times plus minus 0.3. Let's say it's kind of that kind of a difference. Let's put that way. But what I'm quoting is not a change of, let's say, factor of 2. I'm talking about potentially it can be as change. The variation could be as high as an order of magnitude. So that in the end, this M factor will still be within the sensitivity to make the conclusion that yes, this is a scaling as we expected, q squared to the power of 8. Yeah. So it will not hurt us by a lot. We're talking about this being different. Instead of a 4 plus minus 0.25, then we'll get something like 4 plus minus 0.3, something like that.
Okay, thanks. That's enough for now.
Thank you.
Thank you very much. Then I call on the second reader of the proposal. That's Feng Yuan again.
First, thank you for the nice presentation. This is kind of interesting, observable. But if you're trying to put this backward scattering at the same as the level of the GPD measurement, that's just totally wrong, because for the DVCS and also deeply virtual meson production, there are Q-city factorization proof. So that process can be used, those processes can be used to study GPD. But for this process, you don't have any factorization, Q-city factorization. You even don't know how high order correction will be, and you don't know how high trace effects will come in. So it's totally different physics. I'm sure it's interesting, but I don't think it's at the same level as GPD. It's a very general comment. Marcus actually can add more comment on this. Let me go to my question. So you showed Stephen on page 13 for the cross-section estimate.
Yeah.
13. Page 13.
Oh, page 13. Let's see. Yeah, this is page 13, Marcos.
Okay, so the cross-section you show there, class, that's forward, right? Forward pi 0?
No, everything here is all backward pi 0. But you could imagine this is the forward angle. Well, okay, so here you could almost take this as a forward angle pi 0, but scale everything up by factor of 10. And change the U dependent for T dependent.
What's the rationale for this?
Okay. So what we have learned is that in the one rationale is that we have looked at our omega production. As you can see, I'm giving you a the T channel and the U channel omega. What I'm pointing at is the T channel low T cross-section peak and the U channel cross-section peak. You can see that the difference is a factor of 10.
Okay, so that's your basic argument.
Exactly. So this is based on experience.
Okay, so this is no theoretic foundation. I just want to point out, right?
Yeah. And I want to point out, you bring a very good question. If you look at the photo production, and this ratio, the T channel and U channel ratio is not factor of 10. So we don't know what the correct ratio is, but we have taken into account that if this is within, let's say maybe it's a factor of 100 or factor of 10, it's somewhere in there. But based on the electron production data that is existing, it's a factor of 10.
So this actually, what you just said, basically back to what my general comment. So there's, the theoretic foundation for this process is just not there. I mean, for the GPD, you have very solid prediction, but here you don't. So it's can you back to 11, page 11? Of
course.
Again, here it's overstep because there's no rigorous way to connect you to the any tomography picture of the nuclear, because here you are studying so-called, you mentioned about the transition distribution amplitude. In order to study the tomography, you really have to rely on the T dependence. U doesn't play any role here, so this is just overstep.
So here, again, so all our anticipation is that we will see a strong rise of the of the pi zero cross section, as I have shown here for the omega case. You can see that we have 3 points on the very backward angle kinematics showing the clear rise of the cross section, and this anticipation here is based on this anticipation or this observables that we have done for the omega case. And I have to admit that you might be completely correct. You might be completely correct that the hard scattering does not apply in its kinematics. And I would like to go back to the TAC report from the theory side, is that indeed, if we do not see the hard scattering interaction applies in its kinematics, and the soft and non-perturbative interaction should still play a dominant role. So we will still be sensitive to probe that soft interaction process if the hard scattering process does not apply in this kinematic.
Yes, I agree. But the question now, then, what do we learn? Right. I mean, you can put everything into this kind of category that if we don't understand something, we just say that's soft or non-perturbative interaction. And that's not really meaningful statement, because you have to really ask what do we learn from this measurements? What actually improve our understanding of nuclear structure?
Okay, so let me go.
That's a comment. So yeah,
indeed, yes.
Okay, so Marcus, I'm done.
Thank you very much. I think we are running a little bit behind time, so unless there is a very urgent question from any other member of the PAC, that doesn't seem to be the case, then I would like to thank the speaker and all speakers of this session and close the open session for today. We will reconvene tomorrow morning, and the PAC will now reconvene in closed session. Thank you very much and goodbye.